Due to some unfortunate circumstances, I couldn't come. So now I'm there. Yeah, thank you, sir. So yeah, so before that, I hope everybody knows the decoder only transformer. If you like have some conceptual issues on that, please let me know in the comments so I could start from there, or like in the chat. So okay, so yeah, I hope you could see my screen, I guess. Yeah. So yeah, if you look into decoder only transformer, it comprises of the embedding layer, let's say A, and a mass multi-head attention, and then feed forward network. And how do you normalize it? Like there is a lot of methodologies. In GPT-2 and everything, what they did is like they normalize first and then they add next. Or in vanilla transformer, they just put into MHA and add and normalize it later on. Or this thing, I will show you residual, which I haven't implemented because it's giving me stability issues. Um, but I do have a code of it to get you understand what it is. So this is the decoder transformer. So okay, so this is the decoder only transformer. So followed by this, it's going to be a linear unembedding layer. Uh, unem- Unembedding layer. So this session, I will be like focusing more on optimization than accuracy because let's be real, I don't have much CPU. I'm not like really be a rich guy to have much CPU. So I will be fitting this into a single collab instance, like 16 gigabytes of 16 GB of GPU. So I'll be cutting corners whenever it's necessary. So that will take a toll on accuracy and everything. I know that. But the goal of this presentation is not to show the state of the art models, but proof of concept. So that's why. So there would be a trade off. So, but I will encourage to run it in your local machine and then you could tinker around it, whatever you need. So yeah, so the position embedding of it, as I told, I will be cutting corners. I'm using just sinusoidal position embedding. Although it is like inferior, I'm getting position embedding without spending any parameters. So I'm cutting corners over there. So position embedding in is sinusoidal. And other thing I want to say. So if you look into this embedding as well as this unembedding matrix, what you would do is like let's assume like you have 65,000 vocabulary. I took from AI4Bharat Indic Bharat because we couldn't like train it. 65,000, let's assume. So 65,000 and you are like putting it into 1024 dimensions. So this will be the embedding vector's dimension. If you technically look it into unembedding vector, which is going to be n dot linear, would also be in the same dimension. So what you could do is you could manually reference a pointer to point towards here on nn.linear layer, or you could point a pointer to point towards here on embedding layer. Anything works fine. So thus you will be saving 40% or 50% of parameters on your network. It is not ideal to like train in this situation, but given the priority of us, so that's why I tried to do that. And with the first initial thing is completed, I think like everybody understood, and I'll also show code how to do it, so don't worry about it. It's like understood, or is there is anything I wanted to explain in detail on this thing? up to this input thing.
Uh, yeah, sorry. So I just joined a bit late. Can you just briefly repeat the architecture?
Okay, it's just give me a minute. It is it is a decoder only transformer with an embedding layer and position encoding and multi-rate attention and feed forward network. Uh, Feed forward network, yeah. MLP, yeah. So MLP layer, and then you will have a you multiply this in times, and then you will have an unembedding layer here. So to cut corners, to fit it in a single collab TPU, unembedding layer. So I'll come to that point also. So embedding layer converts the number of tokens you have to the set of dimensions. So let's assume like 1024. So unembedding layer would convert your dimensions to a set of tokens you have. So as I couldn't hear you, Surya.
Hello.
Yeah, yeah, yeah.
Yeah, actually, what is that you are like trying to do as a goal? Like because both sides of the transformer, you are like using some embedding and unembedding.
Yeah, yeah.
Like
On embedding layer, like we tokenize it and we'll like convert it into the set of dimensions which we want. On unembedding layer, we'll convert the number of dimensions into the tokens. So we are doing language modeling, right? We have to predict the next token. So
okay,
to get the token, we are using unembedding layer.
okay, yeah, fine.
Okay.
Thank you.
Yeah. Yeah. No issues, man.
So
So
that's kind of a fully connected layer, projecting back to the number of dimensions
yeah, 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 yeah,
equal to number of tokens. Yeah.
yeah.
Uh,
So
yeah.
to
So
cut
any reason means like can you just say means how did you decide the whether to go for decoder only transformer?
so decoder only transformer, it enforces the probability distribution on multimodal on multi-token prediction thing. That's the thing which we are trying to do. Uh, this decoder only transformer has mask, which enforces this probability distribution on predicting next token with the context you have given it, like bigram model. Yeah, I
Okay.
hope it's
So the
understood.
application
Yeah,
is next word prediction.
yeah, like just like language modeling.
Yeah. Okay.
Yeah. So like nothing really new. I'm just saying where and all like cut at corners. So yeah.
Sure. Yeah.
So this embedding layer and this unembedding layer has the same dimensions. So I referenced a data pointer towards here to say that this module and this module is same. So you could around save around like 40% of parameters or 40 to 50% according to your embedding size. Okay. So I'll show you on code how I did it. So there's no issues on that. So then after this, MHA. So I'll come to attention part. Attention part is like same as MMHA, but the thing is, instead of like doing multi-edit attention, we are doing group query attention. Group query attention, what you would do is like I'll show you a picture. Yeah. So this is what group query attention does. I hope you could see it. This is what a group query attention does. In multi-header attention, you have specific keys for specific queries and values. But in group query, you just say that have these two queries interact with this only keys, and these two queries interact this keys. So you kind of like divide it by the group and you do attention operation on it. This saves ton of parameters. This group query attention nearing to multi-query attention, but not like exactly outperforming it. Nearing to multi-query attention while still reducing significantly the parameters which you are using. So this is employed in Llama 3, Llama 3.1, sorry, recent models. So as like if you go really deeper into network, you don't really care about how much values and keys you have. Like you could still be fine with this thing. So this is the attention and feed forward network, which we already know. I don't need to explain it. So without any further ado, let's get into it. So is there is any issue with you with anyone like on this architecture, guys?
It's fine.
It's fine, yeah. So I'll come to the presentation on this. Just ignore this thing. So yeah, the normal imports instead like importing on doing torch view and converting into contiguous value for the sake of readability and everything. I decided to install anops, and from anops like you rearrange the tensor, repeat it, and manipulate it. As I told you in the previous lecture, like the drive link I shared you guys. So so mounting to the Google Drive, just nothing much. Yeah. We'll start from here. So we start from sinusoidal position embedding. The length of the transformer, like it's going to be 1024 sequences, the maximum. Uh, but due to some constraint issue on this, like we are just using 256 for now, for the sake of stability. And the model dimension given here is 768, but I will take like 1024 to match uh, indic bar's dimension, and then you take the position and you apply sine and cos values. That's normal thing. So furthermore, I also implemented relative position embedding. I hope you guys know what's rope is. Sorry, relative position embedding is. So long story short, what would happen is like let's assume we have this attention thing over here. So on K and V vectors, what you would do is you will add a query over there. K plus uh, the position, let's be P. I didn't use rope here, but if someone like wants to tinker with it, you could also use rope over there. So this is GQA. There are like a lot of approaches I thought of it, but on GitHub, like it is efficiently implemented. What I thought was initializing vectors, initializing K vectors, the K groups, and then concatenating according to it and do the multi-error attention thing. But still, what you could do is like assume you have like 1, 2, 3, 4, 5, 6, 7, 8, 8 hits here, 8 hits, and you have two query vectors. So what you would do is let's batch number of it, the token size, and dimension D. So what you would do is same batch. Oh, shoot. I'm sorry, like my hand has batch the number of group vectors, the tokens of it, and the dimension. So what you would do is you kind of like uh, make the shape of this equal to this by just taking out 4 from 8. So you kind of like reshape it into, and and you'll also have a value vector from here, and you apply attention operation, scale the dot product attention on here. So like that, you will get attention matrix. And to enforce this conditional probability, what you would do is we'll assign a causal mask, which is like you could simply do it by saying is causal equal to true. Why did I do this instead of making from scratch? Because this thing, um, scale dot product attention, implements flash attention natively without doing any such trickery. So yeah, you got like really speedy attention with minimal number of code. So yeah, so yeah, the number of the number of modes. If it's MHA, directly do the dot product attention. We don't need to do any transformation. If GQA, as I told before, uh, you do this transformation and you will come back to calculating attention. If it's multi-query attention, it's a special case of group query attention where group the number of queries is just one. So I'm coming down. This is the relative question as a question embedding as I told you before, and you take mix the attention with the number of weights, the same as it. So this is singulated attention. So in the paper, what they did in Meta is, I hope everybody was present in that meet, but I'll just give you a primer. So to predict next token, what you would do is, given the token from first time step to t time step, we'll predict the next token. This is the normal language modeling setup. Um, how this occurs. So how will you predict this thing? You put it into multinomial distribution from the top k vectors from unembedding matrix. Let's assume it's a function of f with parameters u and the transformers function of f, again transformers with the parameters t for now, and embedding of x. So this is how you calculate the next word. Which library is that? I'm not getting it. I'm using PyTorch for this layer. ANOPS. ANOPS is like simple. Okay, I'll show you ANOPS. ANOPS, yeah, this thing. Uh, this is, yeah. So I'll just also share this link in the chat so you could also use it. Like really simple to manipulate tensors. Feels like cheating, but still, yeah, it works. So you take top k. So you take top k and you will put it into multinomial distribution and you'll get the value from it. This is how everything works. On multi-token prediction, what they said is let this setup be as it is. But instead of predicting k tokens on a single inference, on a single model, why don't I make k hits so that what I could do it, I could replicate this k hits and explicitly train on this probability condition like xt plus k given um, so I should predict expl um, the next T plus K token, or else like what to say. So if I'm in the first token, I should predict first, second, as well as third for all Ks. So if K is equal to 1, I will be predicting the second token. If K is equal to 2, I will be predicting third token. And if K is equal to 3, I'll be predicting the fourth token. So on for so forth. So yeah, yeah, you can speak.
Should we not predict, let's say k equal to 2, then we should predict the second and third token together, right?
Yeah, like you'll be predicting together, but uh, the K equal to 1, the at K equal to 1 and at K equal to 2, you will have two separate transformer heads that won't be interacting with each other. The distribution formed by this and this is independent of each other. That's what I'm trying to say.
Got it. Yeah. They're conditionally independent.
Yeah.
Okay.
So these two things are independent of each other. So how will you do that? Because you can't, if you make k heads, like let's assume k equal to 4. So if you're making four heads stacked on each other on the final layer, you could obviously say like I could do multi-head attention and then retrieve it. But the problem is if you started to do multi-head attention on really large dimension, that will obviously come up with stability issues. So in the paper, multi-token prediction, they sequentially run it and they free the gradients. They'll calculate the gradients, sorry. They'll calculate the gradients and they'll calculate the backprop and then they will optimize it. Free the graph by optimize it or step library, step thing. So I'll show you the paper for like let's be on like same page. So this is how you do it, but you don't directly do it. You This is the fundamental, but you won't directly like do it and expect it to work. It doesn't work. So yeah. So I'll come up with the setup on this thing. I have used Tamil language because like I'm really good at. I'm not exactly like really great at Tamil, but I kind of like know Tamil. So, and second thing of it, there is no like active database for Tamil. So I kind of like took it as a challenge to pre-train it, but obviously like it doesn't like work as we expected. So yeah, so I have used Tamil and to make the corpus as quality as possible with minimal number of words and minimal number of efforts for the people, I have taken it from a book called Ponniyin Selvan, which is a really great novel, like 5 parts of novel, and I have taken from it and I tokenized it using AI4Bharat Indic Bats tokenizer, and like kind of like expected it to go. So that's it. That's the experimental setup, and we'll like get into it. Yeah, like so far everything is understood, right?
Hey, so you said that it's not easy to train, and
Mm.
what do you mean by that? So let's say you want to predict four tokens at a time.
Yeah,
So how?
like I'll come on that. Like I'll say on training loop what and all I did to
Okay,
overcome that. Yeah,
cool.
yeah. So I'll go on to this. So these are like this is the thing which I talked about. On this thing, I have implemented a pre-norm. I didn't like do on residual because that gave me some stability issues with the number of tokens I have and the experimental setup. But you could also implement residual if you want. I have written down how to do it down below. But still, I just used pre-norm for now. So I won't be like pestering you with much of this. Okay. So this is like really normal thing. And the only thing which I wanted to emphasize is the independent head that for number of tokens I need to predict. For the number of tokens I need to predict, I need to do single header attention. That's what in this paper also said, the single head. So yeah, and then as I was saying, like how did I connect these embedding layers and unembedding layers as a data pointer? So I simply referenced embed layer dot weight data dot pointer is equal to this pointer, and I like frozen the gradients of embedding layer because I don't want to train it. And then normalization, initialization, just as in GPT-2, no changes, like it works on everything. So I did it. So yeah, first thing, uh, I will have I have did this thing, this implementation on here. I called it as forward trunk, as what they said in paper. First, I put it into embedding layer, and we'll get this size, batch size, and sequence and the dimension. And I will add the sinusoidal position embedding with sequence which I have, and the model size will be 1024 as an AI indic bot, and self dot device will be like what device you are using, like either it's a CUDA or it's a CPU. So yeah, so we add this thing, and you say it as y, and you will add transformer blocks, and you will return that thing at the end of the thing, end of the transformer block, not like adding unembedding layer before unembedding layer. So yeah, this is the forward function. From the trunk, we detach the tensor, like we detach it from entirely. We'll kind of like erase the graph for it, because if you're trying to do backprop on these heads, it will also account on calculating this forward trunk, which will like exponentially increase the memory load which you have. Considering that we are doing gradient accumulation and everything, that will take a significant toll on parameters, and it will cause instability issues. So, and then um, okay, this is just, I'll come to training loop. So this is how I took the model, and from that model, I took embedding dimension and transformer dimension, and I passed it towards it. So three layer transformer with 1024. The number of tokens I'm going to predict is 2, and number of hits in the transformer is going to be 16, and number of groups like 16 hits with uh, two of them, two query interacting with one key and value pair. So that's it. So I'm converting it to CUDA, and I'm just checking the number of parameters. So, so yeah. So this embed layer dot weight. Uh, yeah, number. Yeah, fine, fine. So yeah, I'll come upon this. Let's address the elephant in the room. So from the buffer, what I will do is, oh, I didn't show you that thing. Yeah. So I'm taking the buffer thing, the number of patch and number of tokens I need. From those tokens, I'll just read it and convert it into tokens by NumPy in 32 on using this indic paths tokenizer, and number of sequence and the corpus which I'm having, and I'm just calculating how much iteration I need to do with these tokens and with batch size and tokens. And a taper, I have a flight tomorrow. Thanks, meeting. Yes, sir. Thank you, sir. Uh, so from the pointer, uh, from the let's start with 0. And if I have like batch into tokens like 256, okay, let's keep it the numbers low. So let's assume I have a one batch, and I have um, 12 tokens for each batch. Okay. So what I will be doing is I will initialize them, and then on evaluating, it will be some kind of like on evaluating, this will be some kind of logic. So what I would do is on evaluating, I'll just multiply it like flatten it out, and 1024. And with the labels, what I have, I'll also flatten it out and compute the cross entropy loss. This is how you do language modeling on parallel with transformers. How could you do that? That would be an obvious question if you're like unsure with it. Since the masked attention lower triangular matrix works as this, works as this. On the first sequence, you'll be focusing on this, and the second sequence, you'll be focusing on these two. So you are safe to say that you could just flatten it out, and you won't be having any mixed parameters. So yeah, so that's how like you flatten it out and compute the loss of it. So this is also over, and you convert it into long buffer to data type long, and then. mm, So the batch size is 8 and tokens number sequence of tokens is 256 and the tokens to predict is 2 and then train loader you're just loading it and you're initializing optimizer and I'll like change it soon on optimizer but still like I'm initializing Adam W. Notice with betas 0 0.9 and 0.95 on it is not default settings. On default settings, you will be using 0.99. You're just reducing beta 2 to 0.95. That they do that for stability issues. So yeah, not in paper, like the general practice. I'm talking about general practice here from here on. So yeah, so I'll also come up with this. Has anyone like had any experience on fine tuning an LLM or training an LLM, something like that? Any small experience or anything like if you try to experiment it?
Yeah, I have some experience here, but I'm not
Yeah.
too sure how can I help you in this.
No, sir. Like I'm just asking, like, had you had any experience, like on short and sweet note, like you could share, like on training on smaller batch sizes.
Yeah, specifically on the smaller batch sizes, it's like not very helpful. I have tried on uh, 8 gigs of VRAM on small batch sizes and on 48 gigs of VRAM on a A6 6000. So the
Mm.
difference was quite drastic, and with the larger batch sizes, it's like easy
It's
to,
like more stable. Yeah.
more
Yeah.
stable. Yeah, it goes easy. So
Okay. Okay, so I'll come up on that thing that I actually faced. So how did I tackle that with the constant number of GPUs we have? So, I hope you can't see my face properly. Is it fine or like should I turn on the lights? Yeah, this is fine. Like, okay. So, as Mayank sir said, with smaller batch sizes or 8, 16, or even 64, is not enough with LLM because the LLM parameters are so huge. This batch sizes would be like stochastic update on smaller networks. So we all learned that while doing stochastic updates on smaller networks, it will be like really unstable. Like it will go up and down, and sometimes it will explode. So what you would do in that situation? Uh, you just have constant number of GPUs. You don't have much. What you would do in that situation? We can't do anything. That would be an answer. But what if I say, let's assume like I have a batch size. I need to do batch size of 64,000, and the maximum I could do is 64. So what I could do is do back take loss, do backprop on take loss, first take loss, scale it by 1000 and repeat it 64, right? Repeat it 1000 times, not like just training. Train normally with scaled loss, and then you call loss dot backward, and then as soon as if it's like 64,000, the batch size we decide, like you could do it like modulo operator, you called optimizer.step. Until then, you accumulate this. So you kind of like update it on a bigger batch size, having the same number of GPUs you have. So that's what I did here. So I will not accumulate any. I will just accumulate for 100 steps. I will not do anything. So I'll scale the loss by the accumulation step, and I'll call loss dot backward again and again. And then just don't focus on this now. I'll come up on this later. And then whenever that accumulation steps hit 100, I will normalize it, the grad norm, like have it under 1.0 and perform optimizer.step. So in-depth view of loss dot backward, what would happen is on loss dot, if you keep on calling loss dot backward on one node, it will create a graph. Yeah, now it's fine. It will create a graph here. It will keep on adding the gradients on that graph. It will be keep on adding it. So if you keep on calling loss dot backward, it won't overwrite it. It will keep it in the memory. As soon as you call optimizer dot step, it will free out all the graph. If you have the graph here, it will free out everything. So that's what optimizer dot step does, and it will you will update it. No issues with that. So yeah. So to enforce this probability distribution, as I said before, to enforce this probability distribution, they have proposed this algorithm over here. So you kind of like detach it from the GPU as well as gradient. You won't have any gradient on Z, and you will have D, and you'll enable gradient on that. And then you put D into these model heads, and then while you call backward, D only D would be affected, not the Z part. Z part has like an embedding layer and everything. So if you only affect the D part, you'll get the gradients of the D for a number of hits. So that's what I also did here, a number of it. And then additionally, like I divided by accumulation steps, and then loss dot backward, and I just appended the loss which I had for just like logging purpose. So as far as like the gradients accumulated on D, like let's assume D is here and Z is here, and you have this module dot here, the heads over here. The gradients will be accumulated on D, as this would be like freed out, and you have this here, the Z part. The gradients from here, as rule as back propagation, you just assume this, you got this from here, you got this from here, and then what you would do is like you would do back propagation on D dot grad. So that's what here is done. So give me a minute, once again. Yeah, now it's set. So you accumulate it, and then you do back prop on D dot grad, where it is. Yeah. So yeah, and then as far as accumulation step comes, you could, after accumulation you zero grad it, and for some purpose, some weird purpose, like I don't know, the problem is me or uh, the PyTorch. I think the problem would be on me. So I felt like the gradients aren't like zeroing up. So I manually took model dot parameters after gradient descent. I manually set that into a none. So while doing it, you kind of like reset all the gradients, and while calling backward, it will accumulate again. So yeah. So is there is any doubts, guys?
So this the gradient accumulation is like kind of the way that you do here it here it's like is it uh, while on the experiments that you do here, is it like
Uh, no, sir. Like gradient accumulation, they do it on everything. This is also
okay?
a widely popularly used technique. This is not experimental. This what you do is like it's like saying poor man versions. How to say? So let's assume you have GPU constant here. You can't do anything about GPU. So let's assume we are in that situation, and you have like you could spare out some time with number of GPUs. So you sequentially uh, accumulate gradients on smaller batch size and update it when the batch size hits it's whatever the size you come. So you get it you got it right.
Yeah, yeah. No, I was not asking about the gradient accumulation. I was just
Yeah.
wondering, is the experimental result in line with what you theoretically predicted? Sometimes, like it goes around like in accumulation, those steps or those iterations do not always merge. Like this is the problem. Like I have faced previously. So I was just referring to that. So is the loss curve is
Yeah,
uh,
yeah, like I did it with stochastic thing. The loss curve like moreover loss curve moreover came nearer to it, but still
okay.
like we didn't on stochastic as well as this thing on updating stochastically with larger learning rates. I
Mhm.
felt instability issues like it will explode, gradients would explode. But doing accumulation on larger batches, some stable updates were made, but results were nowhere near like results on both things nowhere near comprehensible because let's say we just have a smaller data size. So yeah, we
Okay.
are
So
building it from scratch. Yes.
so you used a T4, right? 16 gigs.
Yeah. Yeah.
Oh, okay. Okay. Thanks.
So yeah, now I lost my free. Now I lost my free connection to T4. So yeah. So the toll which we add on this setup is like 4.5 gigabits with this transformer module, and then I'll come up on with decoding step. So there is two decoding on said on this paper. First thing, you sample, you just take out every head, like discard it for now, and then you sample one head, like normally what you do on decoder only models. You just take the logits and you just put it on one head and an embedding layer. Take the softmax of it, and you take top 5 probability of it, and then this is due to inference issues. Like I'll solve it later on. I'll also share you the collab notebook. Make sure you also experiment it. Uh, After this, like after few days, I guess, I will convert it into some kind of organized project structure so that it will be useful for everyone. Because this thing is not open source on Meta, so you could see on Hugging Face, but they just wrote only the inference code. So yeah. So you take the multinomial probability value, and then you take the column vector, and then you concatenate. That's it. On independent on this greedy self-speculative coding, what you would do is you parallelly predict on what and all prediction you did, and if that prediction, oh shoot, it's here. Yeah, you parallelly predict what and all you have done. If that prediction aligned with your head of zero, you add those token into that, and then you pass it on to the next iteration. Like if it k is equal to 4 and you want to predict up to 300 tokens, you just take what and all accepted part, and then you'll do it. I'll just show you greedy. Yeah, give me a minute. Yeah. So you do this thing. The So you just take what and all accepted thing, and then from that accepted thing, you kind of like go on with the next thing, next iteration. But on on language modeling, the vanilla thing, what you do is like you predict it, you add it, you predict it, you add it, you predict it, you add it. So you predict this in parallel because since you are using GPU, you can predict it parallel. You can predict in parallel. So how would you do that? So that would be another question. So as I told you before, let's assume the mask of multi-area attention again. So this is up to T tokens, and from the heads you have got K tokens. You add, you concatenate those. You make T plus K tokens, and then you only filter out K tokens from it, and you evaluate with this thing. So that's what I did there. So there is also some kind of like variations of it, given the time constraint and the results. I thought like it is no use of like implementing it. So with generating of one head, this is the context, and I know like this is like really worst. It doesn't make any sense because the loss is around like 5, I guess. Yeah, the final loss is like 0.057 into 100 because I scaled it down, 5.7. So this is kind of worse performing because the number of data we had and number of compute we have to scale on with chinchilla scaling laws, or in llama 3.1 they kind of like overcame it, but still uh, for the worst case scenario, or like the minimum case scenario, what you could do is like you have to scale on chinchilla scaling laws and you have to take number of tokens for it, but given the system which we have, it's not viable. It will be like really long time to do it. So that's why I just kept the dataset sizes smaller and focus more on model part. So that's what here. So on generating one head with multinomial sampling, you got this thing like it predicts us only dotted letters on Tamil, and I furthermore confirmed it by just seeing here. It just predicted dotted words. So still you have to train on larger corpus and you have to train on multiple evaluation metrics from HLSWAG and everything. You translate it and you translate English to Tamil and you translate back again to English to check whether is there is any what to say, is there is any meaning left out. If it's left out, you have to train it, you have to discard it, sorry, and then you have to keep some samples which are which doesn't change from back translating to the English language. So yeah, that's it. So, and I wanted to end this. So good artist copy and great artists steal. So the credits is due to Karpathi's lecture. I took a lot of things from it. The data loader, it's especially his idea, and gradient accumulation. I started to notice on that from his lectures. So yeah, credit is given where it is due. Yeah, thank you. And is there is any doubts?
One question I wanted to ask is, suppose I have a
Yes.
limitation of GPU memory. So what are the parameters that I can control?
So accumulation steps one, if you're doing like you're having like a really big data set, so I will suggest you go on like they say batch sizes here. let's say, so batch size. Okay, 32K tokens. So for 32K tokens, what you would do is, this is the sequence size. The batch size would be around like 1 million or 2 million tokens per batch. So how would you do that? So you multiply B into T, the number of batch into 256. Why am I not getting? Sorry, 256. Okay, I'll just go on calculator here. So let's take 1 million or 1 lakh, 10 lakh, yeah, 1 million. So let's take 1 million. We want to update on per 1 million token, and then uh, you have 256 sequences, but you have to increase the sequences as you have GPUs and 8. So you have to do gradient accumulation of 2048 steps, something like that. Or is it? I think like I made mistake. Yeah, you have to do gradient accumulation on 48 steps, something like that. But 1 million won't be like really. This is why is this is 100,000. I'm sorry, 100,000. Mm. So 1,000, 10,000 lakhs, 10 lakh, and so you'll be doing gradient accumulation on nearly 480 steps or 500. Like let's be but on if you want to build on commercial product, you can't be relying on smaller context sizes like 256 because it's really small. So you have to, let's say, if you want to go on 32,000, and you have just so you have to also increase number of tokens according to Chinchilla scaling laws. So you have to do gradient accumulation on uh, 3090 3,900 steps roughly. So assuming you could fit this thing on your GPU. If you can't do it, then you have to decrease it, either the batch size. But I won't say to keep your hand on sequence size because for if you want to build a really contextual LLM, you have to increase your sequence size.
So what was the sequence that you used for 16 gigs of VRAM?
The 256.
Okay.
Yeah, because like I was really skeptical how it's going to work, so I just kept it down for a while. But now then I knew, so I could like increase it on later thing.
Okay, cool.
Yeah,
So for 16 GB of memory, you basically use 256 sequence length.
yeah, like it's not for 16 gigs. I was not really sure what to use,
Mhm.
so I just started with something smaller, like gut feeling. Yeah, that's the
Yeah. So can
appropriate
you
term.
just give now after observations means
So I
approximately
think like
how much GB, how much sequence length can
so
be?
yeah, that thing you have to look upon how much data you have according to Chinchilla scaling laws and number of parameters you have. You have to consider both things, and you have to come upon with somewhat reasonable thing. Since I have like really small data, I don't really care about uh, predicting long-term things on this model because like this is just a prototype. So that's why I kept it 256. But it's upon your use case. If you want to make something like GPT like thing within your language, I think like making sequence length as much as possible, like uh, let it be like 32K or something, will be a good idea. And even though like you're not going to predict up to 32K and say my sequence length is over, so I can't do anything. You like shift your windows uh, until the necessary length or end of the sentence is arrived. So yeah, so you're not actually bound by it, but you could say like if it's like really larger sequence, then you're kind of like uh, you're kind of like in the good thing. You have like a longer window of attention focusing on. Yeah.
Yeah. So what according to you would be the performance trade-off? Means the more would be the sequence length, the more would be the performance kind of thing.
Yeah, kind of. Yeah, like what I would personally suggest is on your product or everything, first go read on Chinchilla scaling law, and they would like well, what I'm saying, they would like said like 100 or 1,000 times better than me. And then with the data and number of parameters is like established, you could kind of like decide on what kind of models you want to build. Sorry. With the data and number of computers established, you could decide how many parameters your model is going to have. If it's like smaller parameter model, you could keep the sequence length smaller, or if it's like larger parameter model, you could keep sequence length larger on it.
Yeah. So can you please repeat the name that you said? Which
Chinchilla scaling laws.
yeah, please mention over chat.
Yeah, I'm sorry, like I'm not really good at spelling. Chinchilla scaling laws. What they did is like long story short on that paper. I'm not saying take my word for it. What they did is like they evaluated every LLMs available on that, and then they kind of like came upon some LLMs are using way too much parameters on the tokens which they're trained on. Some LLMs use way less parameters than the tokens they trained on, and they kind of like fitted a line which describes what is the optimal number of count to train on this model with arbitrary size x, and they train something called Bloomberg GPT, I guess. Yeah.
Yeah, interesting. Thanks for that.
Sorry, loss. Sorry, I'm sorry, not loss. Law.
Yeah, thanks.
Thank you, Mansu, for the paper. Like, can you just put it on Discord, like later on? Yeah, like any other doubts or any other tips or tricks?
So the first paper that you showed, some faster and better LM. So you followed that paper completely to do this code.
Yeah.
Okay. Yeah.
You
Could
don't
you
have
share
really
that?
have GitHub for. Yes, send you in the chat on our Discord server so that it will be like less hassle. But the thing is, I'll be honest. I thought of like presenting the Discord GitHub version of it, so that will be like really what to say stable than mine. But the problem is this isn't open source. You have one on Hugging Face, but the thing is like you have to sign a research only license. I don't know about it. Like you have to sign that license. I thought like, okay, let's sign it. Let's look into it and then do our thing. And again, it just had inference code. So I just came upon this paper, just read it again, and kind of implemented it. Yeah.
Okay. So whatever the open source means, it's already there on GitHub, right?
No, it's not open source. That's what I'm trying to say.
No, you mentioned that you took the code from GitHub.
No, I was planning to, but the code isn't there.
Okay. Cool. Thanks.
Yeah. So, yeah, no issues, man. Yeah, like, is there is any other doubts? Shall I take it as a no then,
Yeah.
guys? Yeah.
Just maybe a quick comment here. Could you add like a bit of comments here, like
Yeah, sure.
the
Sure,
stuff that
sure.
you have explained is quite nice. I just like I can
Yeah,
understand it, but for the folks that are coming in new, that and the presentation that you will be sharing it, so just add a few lines of comments,
yeah,
like the towards the major functionalities that you are trying to like use on, and like paste it in the Discord server, so that like everybody
yeah.
can
Yes,
uh,
yeah, like furthermore steps should be done, and I'll add comment for it. Like I'll do it.
yeah.
For now, I'll just send the collab link so that everybody won't feel like left out. And then, like when I'll be free, like 2 to 3 days from now, at this weekend maximum, I will make it into some kind of organized GitHub project so that it will be more